Okay, so we've been looking at ordinary differential equations, and we're going to extend these methods to partial differential equations. So the basic same underlying principles based on Taylor series, finite difference methods, but now extended to multiple dimensions, 2D or 3D. So we're going to focus our attention on the Poisson equation. It's a canonical or a standard partial differential equation that arises in a lot of different applications. So in its own right, it's very useful to be able to solve, and it's also a model for other more complicated situations that might arise. So again, so far we've been looking at ordinary differential equations, which apply in 1D boundary value problems. And now we're going to extend this to 2D and 3D boundary value problems, which means we're now dealing with PDEs, or partial differential equations. So we've seen before the Laplace equation, which is partial squared u partial x squared plus partial squared u partial y squared is equal to 0. And then the non-homogeneous version, which has a non-zero right-hand side, is called the Poisson equation. So of course the Laplace equation is just a special case of the Poisson equation when f is equal to 0. So in general, we call both of these elliptic PDEs. And an elliptic PDE is just a fancy word for a boundary value problem. So now we need boundary conditions on all boundaries of the domain. In 2D, that just meant the two ends, A and B, but now it has to include the entire contour, which defines the boundary of the domain. So if we have some domain like this, we're solving for u of x, y throughout the interior of the domain, and so we need boundary conditions at every point on the boundary. And as with the ODE case, they could be Dirichlet, Neumann, or Robin. So a Dirichlet boundary condition in heat transfer context is like an isothermal or constant temperature boundary condition. Neumann corresponds to a specified heat flux, and a Robin corresponds to a convection condition. We saw all three of those cases in the last couple of videos. So we need a boundary condition on every point along the boundary. They could be different. So you could have Dirichlet on a portion, and then another portion has Neumann, and another portion has Robin. But you just have to have a boundary condition all the way around. So now the domain, it's two-dimensional. So in Cartesian coordinates, it's going to be x and y, not just x. So our domain is going to be a bit more complicated looking. Along x, it's going to be the same. It goes from 0 to, say, a, and I is 1 on the left boundary, then 2, then a generic I plus 1, and I minus 1, and then at the boundary is capital I plus 1. Capital I is the first point in the interior. So it's exactly the same as our 1D case, but now we have a two-dimensional domain like this. We'll do the same thing in y. So y will go from, say, 0 to b, and then j will be our index going from y to 2 to generic j minus 1 to j plus 1 to capital J, and then on the upper boundary it's capital J plus 1. And then these grid lines, whoops, that didn't go so well. So these grid lines then look like this as they extend across the domain. And this is why we call it a grid or a mesh, because when we extend all of these, you can see how it forms a rectangular grid in Cartesian coordinates. So now each one of these points where we have an intersection here, 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 and here, and so forth, all the way through, those are the grid points, or the mesh points. We use those terms interchangeably, grid and mesh. So the x domain has been divided up into capital I equal subintervals of length delta x, just like before, but now we do the same thing in y. So y is divided up into capital J equal subintervals to form the delta y. So this mesh then has capital I plus 1 times capital J plus 1 point. So it's many more points, much bigger problem in terms of computer storage. computation requirements, and so forth. All right, so let's consider a second-order accurate central difference approximation to each of the derivatives in the Poisson equation. And when we're in 2D and 3D, we like to, you'll see us draw these quite frequently. We call them finite difference stencils, and so they indicate all of the points for which the solution depends. So at the center, we have the ij point, and then to the right, I plus 1j, to the left, I minus 1j. Above is ij plus 1 and ij minus 1. Then this is delta x, and this is delta y. So what it's showing is, if you go back here, it's just showing for a generic ij point, which is right here, I and j, it's just showing the points on which that approximation depend. So as you remember from second-order accurate central difference approximations for our two derivatives, both second order, one in x, one in y. So those are ui plus 1 j minus 2 uij plus ui minus 1j over delta x squared. Now you'll notice that looks exactly like what we had before, except we've included the j's. So that corresponds to these 3 points. So it's the partial squared u partial x squared is differentiated in the x direction. So it involves these 3 points, which is why we indicate those on the finite difference stencil. Then in the y direction, it looks exactly the same, except now we switch the i's and the j's. So now the i's are all the same, and the j's are j plus 1, j, and j minus 1. So now the y direction, which is the vertical direction, is these 3 points right here. Okay? So the equivalent finite difference stencil in 1D would just be these 3 points. Now in 2D, it includes the y direction, so it involves these 2 points as well. All right, and just as a reminder, of course, these are second-order accurate approximations. So you plug those in. Here's the x derivative, here's the y derivative, add them together, and that's equal to your fij. Just like in the 1D case, fij is shorthand for f of xi, yj. All right, so that's the Poisson equation. Just like in the 1D case, the ordinary differential equation case, we're going to multiply through by delta x squared so that all the terms are order 1. And then we collect all the unknowns on the left and all the knowns on the right. So now the unknowns involve our 5 points in the finite difference stencil, I plus 1j, ij, I minus 1j, ij plus 1, and ij minus 1. And then their corresponding coefficients, as you see here. And then everything we know is on the right-hand side, that's the delta x squared times fij. So again, we now have 1, 2, 3, 4, 5 unknowns, rather than 3 in the 1D case. So it's no longer tridiagonal. We're going to have to use another technique to solve this, but that's our finite difference equation. Once again, unknowns on the left, knowns on the right, as always. Okay, so again, we have 5 unknowns instead of 3, so we can no longer use, for example, a Thomas algorithm to solve a tridiagonal system of equations. So we need a more general technique. And the more general technique, we can go back all the way to chapter 2 to see how these are classified and then extend them to these PDE situations that we have now. Remember, this is step 3 of the numerical solution procedure. So we started with the result of step 1, which is our Poisson equation, that's our governing equation. We did the discretization of the domain and of the equation. It's here and here. So that's step 2. And then step 3 is to solve our system of equations. So if you remember from chapter 2, there's 2 general classes of techniques. There's direct methods and iterative or relaxation methods. So direct methods, that's like Gauss elimination or LU decomposition. Thomas algorithm is direct. So a direct method, there's a set procedure. It has a predefined number of steps. You go through the steps, and after those predefined number of steps, you get the solution. You only have discretization errors. There are no iterative convergence errors. There's no iteration. So there's no iterative convergence errors, there's no convergence test. The only errors are discretization errors. This is very efficient for linear systems of equations where you have a certain structure. That's why we use the Thomas algorithm in the tridiagonal case, because we have a certain structure to it. There's also block tridiagonal matrices, which we're not going to really get into. I've mentioned them before. And the problem is that it becomes less efficient as the matrices get bigger. So as the matrices either get bigger in size or they get more dense, so there's less zeros, less sparse, then these become less and less efficient. It's also difficult to apply to nonlinear problems. So that leads us really to where most of our effort is in this class and in real solutions is in iterative methods. So remember iterative methods, so this is like Gauss, Seidel, SOR. You start with an initial guess, usually just all zeros. You iterate, there's some iterative process that you go through and repeat over and over and over and over again. And hopefully that gives you successively better approximations every time you iterate. Each iteration produces an approximation, and hopefully each of those approximations is getting closer and closer to the exact solution. And that's the convergence process, iterative convergence process. So this does introduce iterative convergence errors in addition to our discretization errors. So now we have both sources of error. That's one of the prices that we pay. But it is generally more efficient for very large and sparse systems of equations. So as systems get bigger and as computers get bigger, we generally have bigger systems. And as we try to solve more complicated engineering problems, they're naturally much bigger as well. And even more importantly, we can solve and adapt these to linear and nonlinear problems. Nonlinear problems will be a little bit more difficult, but we can adapt these iterative techniques without too much difficulty. So we'll look at the Gauss-Seidel method in the next video.